Good evening, folks. Hope you are having a great day. Hi, and welcome to the antenna modeling session organized by the Radio Society of Sri Lanka. Antennas are an important part in ham radio, dare I say, the most important part in ham radio. And like we all know the struggle of finding an antenna design online, downloading it, measuring out the antenna element, lengths and all, fixing it together, trying to connect the antenna analyzer and like seeing whether it works, moving it around, all of that. We like lot of us guys who like to build antennas by ourselves. We really don't know the theoretical aspect of it, and especially with the Foxconn coming up, the RSSL has wisely thought of having an antenna modeling and antenna designing workshop, albeit virtually. So today, the RSSL is very pleased to welcome Mr. Naren Canagasabey, 4S7 November Charlie call sign. Yeah, over to you, Naren.
Thanks, Nadila, for that introduction. Hi, folks. So I'm Naren, as Nadila said, 4S7 November Charlie. I've been a ham since 2008. And just to give you a brief of how this program came about, Ron and Taranga reached out to me a couple of weeks back and said, okay, see, we are having a fox hunt and we'd like you to do a session on antenna modeling. So I've been inactive for at least 6 years, so I thought ideal opportunity to get back to ham radio. So here we go. Right, hope you all can see the screen.
Yeah, no, I can see.
Full screen mode, okay, Nadila?
All good. Yeah.
Fantastic. So again, good evening, folks, and thank you so much for joining today. So our session today is on boosting your fox hunting skills with MMANA-GAL antenna modeling software. So I hope you download the software because you'll need to have it for as we progress in this discussion. So starting off with an outline of this session. So we'll start with some of the terms and the jargon that we'll encounter. And then we are going to look at the desired attributes of an RDF antenna and a general look and feel of MMANA-GAL software. Then the first model, fundamental, I should say, is we are going to design a quarter wave vertical for 2 meters. And model 2 is going to be a quarter wave, a half wave dipole for 2 meters. And then we are going to design our 3-element Yagi for 2 meters for the fox hunt, which will be next week. And then for comparison purposes and to explain a few of the principles of antenna modeling, we are also going to look at a Moxon antenna for 2 meters as well as a 4-element Yagi for 2 meters. Then we are going to move on to antenna construction in terms of materials that can be used and a couple of important notes, critical things to consider when designing your antenna. And finally, we are going to end with a Q&A session. Right, so moving on to the first slide. So some of the terms we'll encounter in this program are impedance, gain, dBi and dBd. So dBi is gain with respect to a quarter wave vertical, and dBd is gain with respect to a dipole. So to put it short, in terms of an equation, dBd equals 2.15 plus dBi. So that's how dBd is worked out. And then we are going to also look at front to back ratio and pattern. Right, moving on. So these are some of the desired attributes when designing an RDF antenna. So the antenna needs to be directional. It needs to be compact and it has to be portable. Moderate gain. Why I say moderate, I will explain in further slides. It should be easy to assemble and disassemble, and it should have a straightforward matching system. Again, will be discussed as we progress. So let's start with a look and feel of MMANA-GAL. Let me share the screen. Right. So hope you all can see the screen. So this is what MMANA-GAL looks like. This is the basic free version, and I hope all of you managed to download and install the software without any issues. So starting off, we have 4 tabs here. So the geometry tab, you can see X1, Y1, Z1, X2, Y2, Z2, and R millimeters and segment. So X1, these are actually coordinates. These are actually coordinates in the X plane, the Y plane, and the Z plane. R is the radius in millimeters of the element, and the segment is the element. And below this, we see sources, number, pulse, volt, and phase. So the pulse is where we are going to enter our source, basically the feed point. And here we see load, pulse type, and you see also inductance, capacitance, and Q, antenna Q. So this we will not use today. This is specifically when adding loads. For instance, say if you're adding a trap or maybe an inductive element onto one of the elements of the antenna, the parasitic elements. So when we go to the second tab called view, here we see the plane actually. You can see the X plane, the Y plane, and the Z plane. Calculation. So this is where we are going to once we plug in the antenna, once we design it, this is where we are going to calculate the resistance, the reactance, the SWR based on a 50 ohm impedance, gain in dBd, gain in dBi, front to back ratio, elevation, and ground. Here you see ground, free space, perfect, and real. So perfect is it's an ideal ground, and real is so you can see you can do the ground setup here. So these two will not be required for today's simulation. And finally, we see what we call the far field plots. This is the pattern. This is where the pattern or the radiation pattern of the antenna is going to be projected. So once all the simulations are done, you will see the pattern appearing here. Right. So first off, let's start with the quarter wave vertical for 2 meters. So as you can see, I've already done this. I've already prepared the model. So okay, so you can see here the quarter wave radiator is basically in terms of formulas 300 divided by the frequency in megahertz into 0.25. So that's how you get the measurement here. So it's 0.5, and I've assumed the radius of the element of 0.8 millimeters. And here you can see the source W1B. W1 stands for wire 1, which is this, and B stands for beginning. So you can see the antenna here. So this is what it looks like. Here you can see this pink circle, that's actually the source, and this box here shows you the dimensions of the antenna. You can see a length of 0.5 meters. And when we move on to calculate, so we plug in a frequency of 145. We select free space, right, and you can see the SWR is 348,606. Now this is because we don't have a ground. So any quarter wave vertical should have a ground, should have a return path for the current. So for that reason, we actually select this perfect ground. So this is the simulated ground. Select this again. You can see the SWR drop to 1.37. And this is the dBi, 5.12. And when we move on to the pattern, you can see you get this perfect circle. And as I move the cursor, you can see the gain is constant at 5.1 dBi. And here you see the sideways plot or the elevation plot. So you can see at different angles from the horizon, you can see the value of the gain. So you can see it reducing here. Right. And for a 3D plot, let me give 3D far field. Okay. So this is what the antenna would look like. Looking from top and sideways. So this is how a quarter wave vertical would radiate. Right? So let's move on to the next model, which is a half wave dipole. Right. So considering the dipole, I always prefer to use to take measurements from the center. So I divide these into half. So you can see I've taken x1 of 0.495 and x2 of 0.495. So this works out to a total length of 0.99, which is 300 divided by 145 into 0.5. So half wave. So which would give you 1.03. So I've made the elements slightly shorter. So here you can see again radius of element radius of 0.8. And here you can see the source is W1 center, which is wire 1 center. Since this is a dipole, the feed point will be the center. So here you see the antenna again. Right. And here we move on to calculation. So here I'm going with free space. And I'm going to start the model. Yeah. So this gives me an SWR of 1.45, and you can see dBd is minus 0.07 and dBi is 2.08. So this is what I actually meant by the dBd equals 2.15 plus dBi. So when we move into far field, you can see what the antenna radiation pattern looks like. So you can see the two lobes. So the dipole would be across the center here like this. If you were to draw the dipole, and you can see the elevation plot as well. So maximum radiation is 90 perpendicular to the plane of the dipole. And if I were to take the three-dimensional far field plot, you will see this. So this is what the dipole would look like. These are the elements. So looking from the top, this is what it would look like. It's basically a donut shape. So there's no radiation from these points, from the ends. You just see this is what the antenna would look like, the radiation pattern. Right. So let me move back to the presentation now. So we did the modeling of the quarter wave vertical for 2 meters and then we did the half wave dipole for 2 meters. Now we are moving on to the highlight of this presentation, which is the designing of the RDF antenna. So if possible, I'd like you to take a screenshot of these formulas. So if we were to look at the Yagi antenna, you have the feed point here, you have the driven element, DRV, you have the reflective element, RDF, and you have the director, and you have the boom. So for this purpose, we are using an insulated boom. So calculations in frequency will be in megahertz. So for this purpose, let's take a center frequency of design frequency of 145 megahertz. So the driven element, one side of the driven element, which is just part of this, it would be 300 divided by frequency in megahertz into 0.473. So these measurements I've actually got off a web resource, and also tweak slightly to improve the gain of the antenna. So these are the measurements that the model is worked on. Driven element is 300 divided by frequency in megahertz into 0.0473. The reflector, one side of the reflector would be 300 divided by frequency in megahertz into 0.495, which is one side. And as for the director, it will be 300 divided by frequency in megahertz into 0.440, which is one of these. And in terms of reflector to driven spacing, which is this spacing, it's again 300 divided by frequency in megahertz into 0.18. And director to driven element spacing is 300 divided by frequency in megahertz into 0.150. Right. So again, back to the presentation, back to the software. Okay, let's open it up. So this is the model I've already done. So let's all work it out together. So if you have the formulas with you. We have the driven element spacing, which is 300 divided by 145 into 0.473, which is one side of the driven element. Okay, that works out to 0.978. So if you divide it into 2, so I have made a small error in the PowerPoint. The driven element 300 divided by frequency in megahertz into 0.473 is the length of the entire element. My apologies. So it's the same for the reflector and for the director. So 300 divided by frequency in megahertz, which is 145 into 0.473. You get 0.978, and if you divide that by 2, you get 0.489. So here we have 0.489. So why it's minus is because I generally like to keep the feed point in the center. I take minus this way. So this element, if we see this portion, it will be 0.4489. And this portion will be 0.489, which gives you a total length of 0.978, which you see here. Hope it's clear. Any questions?
Naren, one question.
Yes, Radhila. Sure.
Where did like how do you find out these numbers, the multipliers? For example, 0.473.
Yeah. So, Nadila, a dipole is essentially so if you divide 300 by the frequency in megahertz, that gives you the wavelength of the antenna.
Yes. Yeah. Yeah.
Yeah. So a dipole is essentially half of a full wave,
Right.
right? And 0.473, how we got 0.473 is generally you tweak the antenna, you tweak the measurements in such a way that to optimize the impedance and the feed point impedance and the gain. So by optimizing these values, by changing them slightly,
Mm-hmm.
you can basically optimize the antenna. So by having, as opposed to 0.5 for a full wave element, for a full sized half wave element rather, by taking 0.473, you're slightly optimizing the antenna.
Understood. Okay.
So
Is
by
there?
adding the
Yeah. Sorry.
yeah, so by adding so these measurements actually have a bearing on the length of the elements, have a bearing on the antenna that we are designing right now. So the Yagi, it has the interaction of the elements has a slight bearing on the dimensions that we've taken.
Understood. Okay. Is it pretty much trial and error, or is there like a standard somewhere?
It's more or less trial and error,
Understood.
Adila. So you'll that's the whole interesting part. So once you plug in
Yeah.
the formulas, you're trying to optimize the antenna. So you just tweak the measurements here and there, and then you see the pattern changing, you see the gain figures changing, you see the impedance changing. So that's actually the interesting part of antenna modeling. So by doing slight tweaks, you're actually optimizing the antenna.
Right. Understood. Understood. Okay. Thank you, Naren.
No worries. So again, hope everyone is clear on how we got 489. So like I said, I generally like to keep the feed point in the center. So I take the measurements along the X plane, and we get a total element length of 0.978. Right. So then element Y number 2 is, this is the reflective element. So to get the length of this, again, we divide 300 by 145 into 0.495, which is 1.02, which is the length of the full element. So you can see here 1.02. So if we divide that by 2, we get 0.511. Again, minus and plus. Here you can see minus 0.372 and minus 0.372. So this is that element. This is the spacing. 0.372 is the spacing from the y0 to the final point. So let me just show you. If I make this 0, you can see how this element has changed. So I make this minus 0.372. So we go back to the original. Here, let's make it minus. Let's make it plus 0.5. You can see how it has shifted. So it's these coordinates which actually define the positioning of the elements. So let's go back to 0.372. You can see the antenna, the element. Right. So again, how I got this 0.372 is 300 divided by 145 into 0.180, which gives you 0.372. So that's the spacing from the radiating element or the driven element to the reflector. Hope everyone is clear on the 0.372.
Yeah. By the way, if you have any questions, like unmute yourself and ask. That is fine. I
Yes,
hope that's fine.
please.
Okay.
Yes, of course. I like if we could have this as an interactive session.
Yeah, looks like no questions so far.
Fantastic. Right. So moving on to the third element. So we have the director. So the reflector is slightly longer than the driven element, and the director is slightly shorter than the driven element. Right. So let's calculate the length of the director. So that's 300 divided by 145 into 0.440, which gives you a total element length of 0.910. So if you move here, you can see 0.91. So to get the length of each side, we divide that by 2, which is 0.455. Then again, minus 0.455 and 0.455. And so why this is plus is this is the minus plane, this direction, and the plus is in this direction, y plus, y minus. So I generally like to keep the driven element along the x plane with y0 and the director y positive and the reflector y negative. So we have 0.31 as the spacing between the driven element and the director. So that's 300 divided by 145 into 0.15, which gives you 0.310. Okay, so just to explain about this radius more. So by increasing the radius, you see a slightly improved SWR over a wider range. So increasing the radius actually has an effect of increasing the bandwidth, the workable bandwidth of the antenna. So the SWR, you're looking at a lower SWR over higher range. So the higher this value, the SWR is going to be lower across a wider range. So the smaller the value, it's going to be narrow banded. Right? And then source,
yeah,
W1 center.
Naren, quick question.
Yes.
So like I understand like getting the radius if it is like a circular sort of rod sort of thing.
Yes.
But I might be jumping the gun here a bit. But since we're like planning to build this with like flexible measuring tape, pretty much, how do we measure the radius of that? It's pretty much
Sorry,
flat.
I got disconnected for a second. If you could repeat the question, please.
Oh yeah, no worries. So like I understand getting the radius of a circular, basically a tube, but how do we manage to like get the radius measurement with something like a flat strap? Like in the case of what we are building for the Foxhunt, it's pretty much like tape measure antenna.
Unfortunately, Nadila, you have to model the elements on a circular tube. So it has to be a rod.
Right.
So it
So
is a very basic software and basic model. So it doesn't give you the option to change the form factor or the cross section of the element. So it's basically a circle.
If we could basically get something like the width and like
Nadila, hope you can hear me. hope you can hear me.
Yeah, so sorry about that. I got disconnected.
Oh, right. I see two hands up.
Yeah.
Any questions, gentlemen? Nadika?
Yeah, Naren, two questions.
Yes, Nadika. Yeah.
One is there the difference whether the element is solid or hollow? That's my question one. And second question, what if the elements are tapered? For example, if you are using a telescopic, uh, those small telescopic antennas as elements, uh, is there any way to compensate that in the software? That's the second question.
Nadika, there is so you can actually reduce. You can have different, basically different sections, but that would uh, would not give you a desired pattern because it takes the elements separately. Let me just show you. Right. So if I were to add here, say minus 0.455. So you can see an additional part has got added here. And I'm going to make this slightly larger, say 1.5. Now the problem is this. So when you press calculate, you see this. So you can see a slight break here. So you can see a slight break here in the current. So to answer your question, Nadika, I've actually haven't tried it with tapered elements, but on models I've done where the section is broken into parts, I generally notice a difference in the model that is generated. I'm pretty sure 4S7RO would be able to add more insight to that. Ron, over to you.
Yeah, sorry, Naren. I'm at work here, so I missed that whole thing. Were you asking about tapering, if that's possible, or what was the question?
Yes. Whether tapering is possible on MANA.
Yes, it would be possible. Like you said, I think you gave the correct answer there. You would have to go to wire edit and break up the elements to, say, 4 parts, 5 parts. I think the possibility is endless. So, say, break it up into 4 and then doing tapering. I think it'll get a little complicated if you were to demo it now, but to answer the question very briefly, it is possible to do by breaking the element. There's a function on the wire edit tab where you can break up the element into endless pieces. So take a 20-meter wire and break it up to 2, 3, 4, 5, 6, 7, whatever, and then you can do the tapering. At least that's how I do it. There might be a better way of doing it, but that's the way I do it now. Naren, over to you.
Right, thank you, Ron. So Nadika, again, what I would generally do is I would take the radius of the largest element and the radius of the smallest element, and I would take an average to keep things simple, Nadika. Hope that's clear.
Yeah, yeah. Thank you, Naren and Ron. Thanks.
Right.
And
And
what about the first question, Naren?
yeah, on the solid element as opposed to a hollow element, Nadika, um, I will need to check on that because I doubt there will be any difference in the bandwidth, but I guess it will only add more weight to the antenna, Nadika. So I need to check up on that. I'm not too sure on that.
Naren, my answer might be flawed, so if anybody has a better answer, please correct me. I'll gladly be corrected. I think because RF flows on the surface of the element, it wouldn't make a difference whether it's hollow or solid. Again, don't take this as gospel truth, but that's my basic understanding. Go with you, Naren.
Thank you, Ron. Thank you so much. So Nadika, let us recheck and get back to you on that. Is that okay? Great. Okay, so back to the antenna.
Before you go,
Yes,
Naren, I
Radhika.
think Sadeepa has a question.
Yeah, Sadeepa, please go ahead.
Sorry to disturb, Naren. I just wanted to add my 2 cents on the element question. So, as per my understanding, the currents travel only on this skin depth. So, if as long as the hollow conductor is containing the skin depth, the thickness, there won't be any difference between the hollow or the solid conductor, apart from the weight of the antenna. So the electrical properties would be the same for hollow and the solid, provided that the thickness of the hollow conductor is greater than the skin depth of the wave's frequency.
Great, Sadeep. Thank you so much for your inputs. Much appreciated. Nadira, do we have any more questions?
Looks like no.
Right.
Yeah, let's
okay.
go.
So let's go back to the model. Right. So let me remove this element for starters. Right. So we are back to our antenna. So now we've calculated the length of the driven element, we've calculated the length of the reflector, and we've calculated the length of the director and their spacings. We've set the source to wire 1 center, which is the center of the driven element. And we've set the frequency to 145. This is free space. Right. So now we are going to start. Right. So you can see the SWR is 1.43. Resistance is 42.27. Reactance minus 14.43. We've got a gain of 5.22. So if I go back to the view tab, here you can see the currents on the elements, on the driven element, on the reflector, and on the director. These are the currents. Here, if we go to far field plot, you can see what the antenna looks like. So if you remember, the dipole had a lobe of the same size on both sides, and you can see by the addition of the driven element and by the addition of the reflector and the director, you can see how the back lobe has got smaller. Right, and you can see the gain, 7.4 dBi, that's perpendicular to the antenna, and how it reduces as you move to the edges. Here, if you take the back, right, and if you were to look at the 3D far field plot, this is what you can see. So this is the driven element, this is the reflector, and this is the director. This is how the pattern would look like from the side. So you can see how the addition of the reflector and the the director, also called parasitic elements, affect the radiation pattern of the antenna. Right, so this is what our Fox hunting antenna is going to look like. And I will be sharing the dimensions as well as I can share the MANA file as well right after the presentation. Okay, so this is what our antenna is going to look like. Right? So, any questions?
Yeah, quick question, Naren. So what is this view? Like, what is the blue lines pretty much?
Yeah, so this is the current. These are the currents on the wires, on the elements.
So, yeah, so the higher up it is, the higher the current.
So you can see
Understood.
the current is highest at the feed point.
Right.
So these are the currents.
Okay. Okay. This might be a bit of a newbie question.
Yeah.
So like the very first antenna I built was Jali's Colombo Special VHF. So in that,
Right.
it was a gamma matching system.
Right.
The outer conductor of the coax was connected to the boom, and it is a conducting boom. So in here, where does the outer conductor go?
So it's like this, Nabila. So this antenna, we've designed it for 50 ohms direct match. So since you're not going to transmit on this, we can do a direct feed. So the center conductor would go to one of these elements to when the outer wire or the shield would go to the other element.
Which one?
Yeah. So, and again, like I mentioned earlier, we are looking at a non-conducting boom, because if the boom is conducting, the antenna would have to be modified slightly, because if we were to fix these elements directly onto the boom, since a small area of the elements would be directly attached to the boom, that would interfere with the pattern and the resulting SWR. So ideally, we would use a non-conductive boom here. But if we were to use a conductive boom, we would need to add insulators to separate the elements from the boom.
Right, but would it still, I don't know, create pattern distortions or interfere with?
Very minor, because again, since
right.
the boom is perpendicular to the elements, Nadila.
Right, understood. Again, to clarify, the center conductor goes to the driven element, the outer goes to?
No, so you can see the driven element is actually split in the middle. So this is one half, this is one half, right? So you would connect one.
Right.
So yeah.
So like a dipole.
Center conductor to one side of the element. So this is basically split into two. This element is split into two, Nadila.
Right.
So one side would be center conductor, other side would be the would be the braid rather.
Yeah,
So-
okay, like a dipole. Okay, I think
Exactly.
Ron has his hand up. Ron, go ahead.
Yes.
Yes, Naren, if the element was to be continuous with no split for ease of construction, then where would the braid go?
If the element was to could you repeat that, please, Ron?
If it was a continuous element without a split in the middle, then would you need something like a gamma match, or how could it be matched? If
Yes.
I'm asking the question because it's a Fox Hunt antenna,
Yes.
so say to make the construction simpler and
Yes.
sturdy,
Yes.
can we possibly have? I'm not suggesting I'm asking a question actually. Can the driven element, be one continuous length without a split in the middle? What complications would we face if we do that?
So I would think, Ron, that if we were to make the driven element a continuous element, we will have to go for a matching system. Maybe, for instance, a gamma match. But that may add some complexity to the antenna, I'm guessing.
Yeah, possibly, Naren. I think though, because the center is at ground potential, so you
Yes.
can, whatever you do, you can connect the braid there, Nadila. But then our problem will be, where do we connect the inner to tap to the 50 ohm point? Then, like Naren says, we need a matching system. I think we got that clear. Go ahead, Naren.
Thank you, Ron. Nadila, any questions? Or anyone else in the audience?
No. Yeah, anyone else?
So-
Just go ahead. Unmute yourself and go ahead. Looks like no.
So we could, to answer your question again, Nadila, we could go for a matching system like the gamma match or T match or hairpin match. But to keep matters simple, since we are not doing any transmissions, we have gone with the direct connection of the coax to the driven element.
Understood. I think Nadika also raised his hand now. Go ahead,
Yes,
Nadika.
Radhika.
Yeah, Naren, now if we are splitting the driven element in the center, what's the best, the gap between the two parts of the driven element? The center gap. I don't know what you call it. The gap between the
Yes.
two driven element parts.
Yes. So, Nadika, what I've usually done is when I've used aluminum elements for the center conductor, the driven element, I generally use a spacing of around approximately 1 centimeter between the two elements. And to add a little, to make it a bit more sturdy, I usually take the center, if you take the RG213 cable, the center insulation, because that fits perfectly into a 3/8 diameter aluminum tube. So I generally use that to give a little added strength to the antenna, to the center elements, Nadika. But I generally keep around 1 centimeter, half a centimeter to 1 centimeter between the two elements.
Okay, thanks, Naren.
Ron still has his hand up. Anything else to add, Ron?
Oh, sorry. I need to put my hand down.
Oh, right. Okay, no worries.
Right. Okay. So let's move on. Now over to the comparison antenna. So we'll start with a Moxon antenna for 2 meters. Let me first show you what it looks like. Okay, so this is the comparison antenna. It's a 2 meter Moxon. So a Moxon is generally, it's actually it's similar to a 2-element Yagi, but to make the antenna more compact, the elements are slightly bent inwards at the edges. You can see this is the driven element and the reflector also. Now there is actually a calculation program, sort of a software which has been developed by a ham for calculating the dimensions of a Moxon antenna, which I will share with you. This is another great antenna which I've used in the past. Very easy to build. So you can see there's this small gap. This is, again, the calculator gives the exact spacing here, which is critical. We go back to the Moxon design. So you can see here's a 2-element Moxon which I have modeled based on the modeling, the measurements given by the modeling software. So you can see these are, so here we have the separate elements. So these are separate segments. So you can't have bent elements in MMANA-GAL, so you have to add these as separate wire segments. Right. So we have the feed point here. Let's do the calculation. So we have again over a dipole of 3.91 dB. This is the distribution of the currents on the wires, on the elements rather. And let's go to the far field plot. Right. So you can see what the slight change to the antenna, to the Yagi has done. So here we see the back lobes are significantly reduced. We see slight side lobes starting to appear here. The back lobe has significantly reduced, and you can see how the front lobe has got wider. It's bigger, it's wider. Okay, if you go to the 3D far field plot, this is how the antenna would look. You can see how the back lobe is significantly smaller and how the front lobe is wider. Right. So let me show you something else which I couldn't show you on while doing the previous models. So if I go to click plots here, center frequency of 145, just going to keep these as is. Go to click SWR here, and I'm going to click all points here. So you can see the SWR curve of the antenna from 143 to 147, the 50 ohm feed point impedance. So if I were to increase the bandwidth, say 8000 kilohertz, you can see how the SWR is distributed. Gain figures, the far field plots of the different frequencies. Again, for comparison's sake, let me take the 3-element Yagi out again. So let's plot on 145. Let's keep this here. Let's go to SWR, click all points. So you can see the SWR from 143 right up to 147 is below 2, the feed point impedance of 50. again in the front to back. Here you see the pattern. So by playing around with these dimensions and using this SWR plot, you'll be able to design or optimize your antenna for the desired frequency. Okay, so moving on. Okay, so going back to our model 4, which is a 4-element Yagi for 2 meters. This again is for comparison. Right, so we have our elements here. For this, I've actually taken the measurements from a website called DK7 Zulu Bravo. He's made quite a lot of antennas. So I've taken measurements of that side. See, we see the radiator. And if we were to go to the far field, to the calculations, we'll see SWR of 1.03 and how the gain has increased to 6.07 dBd. You can see the distribution of currents, the elements. And if we go to far field plot, you can see the pattern. You'll notice how the forward lobe has slightly narrowed, and you can see the appearance of side lobes. So for a fox hunting antenna design, we like to keep the side lobes to a minimum. But the issue is that if we increase gain, if you want to increase the gain of the antenna, the side lobes get more pronounced. So the side lobes start gradually shifting in this direction, and you see nulls. So this would be a null where the pointer is now. So you see the side lobes shifting to this side, and you see some nulls in the pattern. So that which is not desirable. It makes the antenna more Let me see if I can show you an antenna with the nulls. So these are models which come with the software. Let me take 12L1 430. So here we see 13 element modified Yagi. The calculations. Okay. So here you can see the nulls. This is what I refer to by the nulls. Dips in the gain. So if we were to see the 3D far field plot. Right. So you can see in these areas, these are the nulls. So the pattern becomes more narrower, but also brings in nulls.
Right. Naren, I think Ron has something to add.
Yes. I'm sure Ron will be able to elaborate more on the pattern.
Oh no, not to elaborate. Just a question, Naren. Now, having looked at that multi-element, I don't know how many elements it had, and the side lobes, would you still say, regardless of the gain and the narrow front lobe, would you still say that your choice of an RDF antenna would be Moxon or the previously designed 4-element layer?
For convenience sake, I'd like to go with the Moxon since it's more compact. But the 4-element, I would not go for the 4-element because it's a bit. One thing is it's more cumbersome. It's less portable. It's a bit cumbersome to carry around, and maybe a bit too much gain also because like we had the discussion a few days back. It's going to the closer you get to the fox, it's going to
Saturate
basically
your receiver.
saturate
Signal is
your
going to be
receiver.
too strong.
Exactly.
So a follow-up to that question. So looking at the present design, I see a very narrow front lobe, but there's quite a bit of radiation off the side of the antenna. So would I be correct in assuming that this antenna, regardless of the narrow front lobe and the higher gain, would not be as desirable as the Moxon?
Correct. Definitely.
Thanks, Naren. And one last question. Sorry to take up your time. I'm using my phone, so I've not been able to zoom in on figures. Did the Moxon have more front to back than the 4-element?
It did, Ron. It did.
Okay, thank you. No worries.
Yes.
Continue now. Thank you.
Right. Okay. So
I think Nadik also has that.
yes, Nadika, please go ahead.
Naren, and just want to add about this Moxon. A good thing about Moxon is you don't need any matching. You can directly feed it to the two element, I mean, the two wires of the driven element.
Exactly, Nadika.
Yeah, that would be a added advantage, wouldn't it, Naren?
Definitely, Nadika. Definitely. And I've also seen a couple of designs with. Let me see if I can share those later on. A modified Moxon with additional driven elements. Sorry, with additional directors. So let me see if I can get those the designs out and share it on the thread. Right. So going back to our presentation. So in terms of antenna construction, for elements we can use tape measure, a broken or no longer use tape measure, which is very convenient, very portable. We can also use welding rods. I've used welding rods in the past for 70 centimeter antennas and also 2 meters. Coat hangers is another option, and of course aluminum tubing. But again, the like we mentioned at the start, the objective is to have the desired attributes rather of RDF antenna would be compactness, portability, and ease of assembly and disassembly. So these are some of the materials you can use for the construction. For the boom, you could of course use PVC pipe. You can use aluminum tubing. So these are some of the materials that you can use for construction. Okay, so moving on to important notes. So these are some things that I've learned the hard way. So whenever you design your elements, it's always better to cut the elements slightly longer and trim it bit by bit until you achieve the desired SWR. So this is mainly for transmitting antennas. So in the past, I have cut the elements, being a bit rash and cut the elements, made large cuts. So unfortunately, you ruin the antenna that way. So it's always better to trim bit by bit until you get the desired SWR. So another good point that Ron also brought out is over-optimization usually results in low feed point impedance. So by trying to improve the gain, impedance, and front to back ratio and pattern, it can have an impact on the efficiency of the antenna. So it's always a better idea to strike a balance between gain, impedance, front to back, and pattern. So that's why at the start itself I mentioned moderate gain. So it's a compromise between gain, impedance, front to back, and pattern. And like I also mentioned during the modeling sessions, nearby conductive elements will definitely alter the pattern. So say if you're mounting the antenna, a Yagi antenna vertically, if it's a metal mast, it will definitely affect the radiation pattern of the antenna. So as a rule of thumb, I would always advise that if you're mounting the antenna vertically, you use a non-conductive mast, at least say a foot or two below the antenna. So you ideally you should attach the antenna boom to a non-conductive mast if the antenna is used in the vertical polarization. Right? So that's for the modeling session. And any questions from the audience?
Yeah, feel free to unmute and ask.
Okay, let me stop sharing.
Okay, one question from me, Naren.
Yes, nothing.
Suppose we are modeling something like a loop antenna on MMANA-GAL. Can we do that? Can we like have curved elements like that?
Definitely. Let me show you.
Yeah.
So another favorite of mine, Nadila, would be the cubical cord. Fantastic antenna, but
Right.
a little difficult to construct. Fantastic antenna though. Low noise, wide bandwidth, but a bit difficult to construct. Let me
I see.
go back
Okay.
to a VHF antenna.
Cubical cord is directional though, isn't it?
It is.
Right. Same with the loop antenna, I guess.
Definitely. So a cubical cord is essentially a loop antenna, Nadila.
I see.
Yeah. Let me see if I can get the. Yeah, I think we had one on the VHF beams. Yeah, here we go. You can see cubical cord. So basically,
Actually, you aren't sharing the screen.
oh, sorry.
Yeah.
My apologies. Hope you can see the screen, Nadila.
Yeah. Now we can see.
Right. So here we can see a cord, cubical cord. So each of these elements is different. You have to plug in these elements separately. So you can see there's a total of 12 wires. So bit complicated to model, but fantastic antenna.
Understood.
And only thing is, Nadila, as with a cubical cord, you can't do a 50 ohm direct match because the impedance is somewhere around 150 to 200 ohms. So you need to have a matching system if you are going to transmit.
Right. So something like a transformer.
Definitely.
Understood.
So you can see the pattern here. So
I'm just curious. Sorry, go ahead.
Yeah, please go ahead.
Just curious if they could do a cubical cord for the logistics aside, whether we could do it for the fox hunt.
Oh, definitely.
Right, should try.
Definitely. So it's actually one of my favorite antennas, especially for HF. Very low noise and bit difficult to match. Not all that difficult. So, but compared to Yagi, a bit more difficult to match. And of course, it has a bigger effect on your wallet as well.
I see. Okay, so how are like the antenna length? Sorry, the element length.
The element lengths, Nadila, again, if you take the circumference or the length of of these elements, it will be a full wave.
I see. Okay, okay.
So this is 0.25, 0.25, 0.25, and 0.25. So you get a full wave. And the reflector, again, like a Yagi, the reflector is slightly longer. The director is slightly shorter.
Understood.
And but it's a fantastic antenna. And I remember 4S7 Echo Alpha rather. Echo Alpha Ernest used to have a fantastic HF 2-element quad for 20 meters to 10 meters.
So it could be multi-band as well. Interesting.
Oh, definitely. So basically, Nadila, you can have a common feed point, but there will be slight interactions between the elements because you're transmitting through all these elements. So there will be slight changes in the pattern. But yes, you can have a multi-band quad for sure.
Right. Okay. How about circular elements?
A bit complicated, Nadila.
Understood.
Because unless you have a very stiff wire, of course, a circular element would give you more gain because the cross-sectional area is much larger. But logistics side, it will be a bit difficult to construct.
Right.
So,
I'm sorry. I think I'm sorry.
Or a delta loop, for instance. But by making the cross-sectional area smaller, it has an impact on the gain of the antenna.
Understood. Okay. So if you're modeling like a circular element, is that possible in MMANA-GAL?
It is possible, but it will take you a long time because to get. Let me show you. I think there was a. I think there was an element. There was an antenna which was a helix antenna. Oh yeah, here we go. No, sorry, not the helix. It's a loop antenna.
So pretty much short lengths of straight wire, isn't it?
Yes.
Right. Okay.
Here you go.
Understood.
So this is what happens. Of course, this is not a. It's not a loop antenna because.
Right. It's more like an octagon.
Yes, exactly. But it's a bit difficult to construct, Nadila.
Understood. Okay. Any other questions, folks? Okay.
Just one question, Naren.
Yes, Taranga, please go ahead.
Please ignore this if this has been already answered or shown. Is it possible to create 3D radiation patterns using the software?
Yes, Nadila.
Not
yes,
like the
Taranga,
cross
of
section,
course.
but yeah.
Of course. Let me show you. So let me take the Moxon again. Okay, here you see the 2D pattern, and if you click 3D far field, get the 3D pattern. Hope it's clear, Taranga.
Thanks, Naren. I'm sure you must have shown it earlier, but I joined it
No
late.
worries at all.
I think Ron has something to add.
Yes, Ron.
Yeah, Naren. I noticed you said that you took the 4-element from BK7 Zulu Bravo.
Yeah. Yes.
but I must compliment you on the tweaks that you have done. I don't think the original DK7 Zulu Bravo had that same pattern. I think you've done some work to reduce the side lobes, so you've done a great job. I just want to break in and compliment you for tweaking it in a way that it's ideally suited for RDF. Good job, Naren.
Thank you, Ron. Thank you so much.
Would it be possible to show the changes or the optimizations you did to that to the original design, right?
There were quite a few changes done in terms of the spacings, Taranga.
Okay,
But
right.
I can share the workings on the WhatsApp group along with the files.
Okay, superb. Thank you, Naren.
What
Thank
I
you, Ron.
suggest is, sorry to break it. What I suggest, Taranga, if you're getting started out or anybody else is getting started out with this software, just design a basic, say, a two-element Yagi, and like Naren said, move the spacings around and then quickly have a look at the radiation pattern and see what happens to the front lobes and the side lobes and the back lobes as you change the spacings of the elements. That would be a good way to learn how radiation patterns changes would change with regard to the different element spacings.
Right. Thanks, Ron. And just one more question, Ron and Naren. Does the software allow to design your own matching networks as well, or do we have to do it separately? And is there a way to bring bring in pre-designed machine networks to the software? Is it possible, or is it just the antenna that we can design only?
So, Taranga, let me just go back to the software. Here you can see this section called loads. So if I were to take, say, for instance, let's say an HF simple vertical, uh, let's say ground plane, for instance. No, wrong choice of antenna. Just a second. Let me. Uh, so there is a way that you can. Okay, let me take multiband. Say a trap dipole. Okay, so here again you can see under loads. Basically, you can add a trap LC network. So even to the feed point, you can make slight adjustments to the inductance and capacitance, but it doesn't have a it doesn't have a an ability to design a matching system as such, Taranga.
Okay,
Ron, any
Naren.
comments?
Right, got it.
Um, yeah, well, indirectly you can, like you've demonstrated. So what you can do, Taranga, say rough approximation, okay?
Yeah.
Say a 40-meter vertical would be, say, 33 feet long,
Hmm.
and then you have space only for, say, a 20-meter, and you
Mm-hmm.
want to bring it to resonance. So,
Yeah.
like Naren said, you can go to the loads and keep adding L and C till you reach resonance. So to that extent, you can do matching networks. There's a lot in the software. You can even model an antenna with a coax cable. Honestly, I don't know how to do it. It's complicated. I haven't tried it. That is possible. But a simple answer to the question, yeah, you can do things like impedance matching and add a trap coil, like Naren said. So you can design a dipole and add 2 trap coils and keep changing your LC ratio until you say trap a certain frequency and say design a dual band dipole antenna. So yes, you can do it.
Okay, Ron. Thank you.
Any more questions?
Looks like no. If you have any questions, just unmute and ask.
So to summarize, Naren, say you're on my team, and I say, Naren, build an antenna and bring it. Meet me at the DF tomorrow. Would I be correct in assuming that you rock up with a Moxon?
I think for ease of construction, Ron, I might go with a Yagi, because might be a bit difficult to bend the elements, if you know what I mean. But I would love to go with a Moxon, but say if you're using aluminum tubes, then it would be a bit complicated unless you have a bender. But if you go with
Welding
for
rods,
instance,
maybe?
welding rods, yes, definitely, yes, of course.
Yeah. And then, of course, the center, the insulator between the two elements, you'd have to sort of,
Yes,
use your imagination to get
yes,
around that problem.
yes. I've seen so many designs with an electrical connector being used.
Oh,
As
yeah. Beautiful idea. That's right. Yeah. Why not? That would be the best if anyone's considering the construction of a Moxon
definitely,
for
definitely,
field
because
day.
that also
Terminal block,
has
yeah.
exactly.
Oh, yeah, that's right. Yeah, great idea. I think though the superior front to back on the Moxon, I think a, a 2-element Yagi does not have the same front to back as a 2-element Moxon, although they essentially a Moxon is a Yagi with bent elements, isn't it?
Exactly, Ron. Exactly.
So
And I
why
think
is it that the
the
Moxon
Moxon has
has
slightly more
superior?
gain also, right?
The gain I think is slightly less, just a fraction less, but it has better pattern and front to back, and also the ability to match it directly to a 50 ohm cable makes it a very attractive antenna for any band. For example, I had a wire Moxon rectangle on 40 meters for many years, and boy, that thing really worked like a bomb. And even Nadika has played around with 20 and 15-meter Moxons, and we swear by it. Great antenna. Go ahead, Naren.
Right. Thank you, Ron. Thank you for your inputs. Nadika, yes, you have a question?
Yeah, Naren, what's the insulation part you said that you have seen on somewhere for Moxon?
It's an electrical terminal block, Nadika, or electrical connector.
You mean what goes inside these concrete slabs?
No, the electrical. Okay, let me show you.
Nadika, those bars you have, like you have transparent cover and a copper piece with 2 screws inside, and you have set up those.
Ah, right. Yeah, yeah.
I think I may have accidentally muted Sandika. Sorry about that, Nadik.
Oh, I'm referring to the. Okay, just a second. referring to these, Nadika.
Yeah. Okay. Thanks, Naren.
Any more questions?
Looks like no. If you have any questions, like just go ahead, no problem.
Okay, I'll preempt the question. Naren, at the start, we were discussing these numbers 0.5, 0.49, 0.48. So, can you briefly explain why those numbers are different and what the significance of the 0.5 is? I know that's because 0.5 of a wavelength half wave dipole. Now, that 0.5 becomes 0.4 something. Is it only because of optimization, or I think it has something to do with the velocity of propagation as well, isn't it?
Yes, of course. Yes, of course. Yes, of course. So, if you're using narrow elements, it would lead to a slightly higher value, Ron. I hope
Yeah,
that's
that's right. That's just to clarify. So, I mean, a half wave dipole is never a real half wave in free space, is it? Because of the velocity factor. And also, if the y is inflated, then it becomes a little shorter. Now, we're talking about VHF antennas, but in general, what I do is, we have that famous formula 468 by frequency. What I do is, I multiply that by zero point 0.5 to get a more sort of workable length for a dipole because of the velocity of the insulated wire.
exactly.
So, would it be fair to say, if in like a theoretical sense there was no cross-sectional area of the conductor or the element, it would approach 0.5?
If there's no cross-sectional area.
Yeah.
So, Nadila, the larger the cross-sectional area, the closer it will approach 0.5.
I see. Okay. The other way there.
Yeah.
So, Naren, what difference does it make when using a tubular or a hollow conductor versus a solid or rigid conductor like a welding rod or something? So, is there a difference, a significant difference? Oh, which one would you
Uh,
prefer?
a hollow tube as opposed to a solid.
Yes, like an
Yeah.
aluminum tube
So
versus a
yes,
welding rod?
yes, yes. Again, Taranga, it was also covered. Just to reiterate, it was covered during the session, but just to reiterate, as since the current travels along more or less the surface of the antenna, of the element rather, and I think one of the guests pointed out that as long as the thickness of the element uh, is of a certain depth, it doesn't have an effect on the antenna, taranga, because the currents usually travel on the surface of the element.
Okay, Naren, thank you so much. I definitely need to go through the video again. Sorry about that.
No worries at all. Any more questions?
Looks like that's it. If you guys have any other questions, please go ahead.
Okay, so I think I have a question for everyone. So based on the two designs we modeled today, the um, 3-element Yagi as well as the Moxon, what is your preferred choice? Is it the Moxon or will it be the 3-element Yagi?
Okay, let's do this. If it's a Moxon, raise your hands.
What was the boom length of the 3-element, Naren?
The boom length, Ron, was approximately 0.7 meters.
0.7, okay. And the Moxon would be about half of that?
Definitely, yes.
So the Moxon had a better front to back and a front to side ratio, but it had a broader front lobe by virtue of the fact that it's got only two elements. And the third element of the Yagi narrowed the front lobe a little bit. Am I correct in making that assumption?
Correct.
Okay. I'd have to, when you send the files through, I'll have to look at the 3 dB, the width of both antennas. And I, you know, I might take a chance with the Moxon because of the portability. If I can put it together with electrical terminal blocks and welding rods, it'll be very easy to manage, and it has a beautiful, rejection of the side and the back. So even though the front lobe is broader, I'm quite confident that I might be able to nail the Fox because of the superior rejection of the back and the side. But that's my personal choice. I don't want anybody to think, oh, Ron said he'll take a Moxon, so that's all we are going to build. It's my personal choice, and I thought I'd just throw that out.
Thank you, Ron. Thank you. Okay, so I think we have 3 or 4 members who've decided on the Moxon. Fantastic.
Yeah, it looks like we have reached our time limit as well.
Yes.
If anyone has any other questions, final call. Go ahead.
Okay, I'll grab this final call for myself. Thanks, Naren, for accepting our invitation. You've done a fantastic job. Trust me, I couldn't have done it better. So thank you very much for taking the time out to come and share your knowledge and experience with us. I personally learned quite a bit myself. Trust me, I'm not just buttering you up. I say that very sincerely. So thanks again, Naren, and over to Nadila.
Okay. Yeah. Again, as Ron said, and actually Ron and Naren both, thank you so much for agreeing to host this, participate in this session and share your knowledge with us. I hope everyone got to grips with the software, at least as a beginner. I'm sure I'll be trying it out as soon as this is over. And just a reminder, this will be available on YouTube. It is being live streamed right now, and it will be available as a video later. Hope you all had fun. Again, thanks Naren, thanks Ron, and a big thank you to Jalia and Taranga for organizing the whole event. And there are a lot of members of the RSSL who aren't here that who took a central part in organizing all of this. I think we can't go through all of them, but again, thank you everyone for being here. Okay, that's it. Let's wrap it up. Thank you.
Thanks, Nadila. A
Bye.
special
Good
thank
night.
you to Taranga and Ron for giving me the opportunity to present this. And also Ron, because he's been my antenna Elmer for the past, 10, 12 years at least. And always supportive and always willing to share his ideas. So special thank you to Ron. And thank you, everyone. Thank you so much for joining in. And hope the session was useful. and good hunting on Saturday. Thank you.
Thank you,
Naren, thank
Naren.
you so much. Ron, thank you. Naren was so humble and too modest, I believe, that he said uh, he's not a master of the subject, but I'm sure that you all witnessed how what a master he is.
He
And
clearly is. Absolutely.
thank you, Naren. Thank you so much. He did all this in such a short notice, Nadila. So it has to be appreciated so much.
Absolutely. Yes. You can't fake expertise.
Uh,
And
thank
thanks,
you, Naren.
Nadila, as well. You've done a great job again.
No worries. Utpala, you had something? Go ahead.
Thank you, Naren. That is a very good chance you give us.
Thank you, Utpala. Thank you, Taranga, and Nadila. Fantastic job.
And a big thank to Binet also for standing by and streaming this to YouTube. There
Yes,
are
of course.
there aren't so many resources. There are not many resources in YouTube for this modeling software, Naren and Nadila, as you may have already searched. So this,
Yes.
I'm sure that this would be a valuable resource for not only for us for SHAMS but for hams worldwide as well. So thank you so much.
This might actually pick up, no, Taranga? We might get some
Yeah,
traffic
yeah, yeah.
actually.
We'll see.
Okay, folks, then that's it. Good night. Thank you for joining us.
Thank you,
Okay, good
everyone.
night,
Good night.
Naren. Good night, Naren.
Good night, everybody.